Okay, I guess we'll start. So what I did last time was to define a way of building equations of motion for active systems. Let me start my screen share. Second. Yeah. So what I did was to argue that just a second, this is not the page I wanted. Yeah, what I did was this seemingly complicated process where I said that if we have variables for which we know the equations of motion and we identify one subset of those variables and call them the chemistry and drive them, then we get these emergent equations of motion in which there are extra forces proportional to the degree at which you're driving the chemical degree of freedom, and whose form is such that in general, you can't reabsorb it into the original equations governed by Hamiltonian. So in that spirit, basically anybody can give me the equation for any system obeying dynamics of equilibrium. And in a general sense, I know how to modify them to look at new out of equilibrium dynamics. So I'll skip all these complicated things. And what I argued was, and let me actually skip ahead a little bit to a slightly easier version of this story. Supposing I had a bunch of objects like this that like to line up with each other. Okay? Supposing each little pointy arrowhead has a rule that says it wants to line up with its neighbors. So this green guy has these 6 blue neighbors. It has a neighborhood of defined size. And at the moment, let's not worry about the other interaction. Let's not worry about separation. Let's not worry about cohesion. And let's right now not even worry about the fact that these are arrows that are moving. Imagine they were just arrows that were pointing in some direction. What equation of motion might one construct for these? I argue that in a general sense, the equation of motion that you would be inclined to write down for a system like that would be, and of course I'm losing the equations, just a second. Would be that if I coarse-grain all those little arrowheads, I'll get a vector field E. The interactions that made those vectors line up with each other, when coarse-grained, will give me a smoothed free energy functional in which the fact that if the noise was low enough in that system they want to line up is encoded in a coefficient A, which decreases and becomes negative when you make the noise low enough. And this functional, then, if A is negative and B is positive, will favor P being locally non-zero and will favor neighboring P's pointing the same way. So if these guys were just little arrows pointing in some direction and representing, for instance, a bunch of mechanical rotors at thermal equilibrium, you'd get a dynamics like the Ramaswamy equation I wrote down for one particle that says that P evolves by trying to go downhill in this energy and by being kicked around at random by a noise. Okay, now the next part of the story is we can take this very system and say, hang on, there's some noise outside, sorry. Yeah. Now, what you can say is, supposing this system is now in some driven state, maybe you want to think of that driven state as arising from the P's themselves moving, or maybe you want to just say that the P's are in some general state driven out of equilibrium. then I'll say by my general prescription, I can add to this equation something proportional to the strength of the chemical driving times a general function of the P's and gradients of P, which has to respect the fact that P is a vector. So I have to add vectors of a general form. So what kinds of terms can I get? Well, I can get two kinds of terms. I can get vectors of the sort that would come out from this del F over del P, which means I could get P, I could get P dot P times P, I could get del squared P. And then I could get terms of a wholly new type that don't figure in the list of terms that could come from an energy function. And the simplest of those is P dot grad P. Okay? The moment you get this term P dot grad P, this equation is changed in a profound way because this term says local disturbances in the P field get carried by in the direction in which P is pointing. Okay? So P acts like a velocity field, just like the V dot grad V nonlinearity in the Navier-Stokes equation. The interesting thing is that if you take this model and put in essentially the aligning tendency and a rule that says that the direction in which these guys are pointing is the direction in which they move, you will end up getting that dynamics. If you take that kind of kinetics, that is, if you take a kinetics in which you have particles, each of which has a position and a direction, aligns with the mean of its neighbors plus a bit of noise, and then moves in the direction in which it's pointing, and coarse grain it, you will end up getting equations of exactly that form. You will also end up getting a coupling to the concentration, as I said last time. So this is the pair of equations you'll get. Okay, I probably have notes there. All right. So let's spend a few minutes understanding these equations, because these equations set the stage for what I want to talk about, which is when this kind of tendency to align and move happens in a fluid medium. Right now, I'm ignoring any kind of ambient fluid. I'm just saying I've got these little vectors. I'm defining a field that has some of the properties of a velocity field from these little vectors of the particles. But I'm not worrying about the fact that they're surrounded by a fluid, that if one of these agents moving through a fluid slows down, it has to give momentum to the fluid. That momentum will affect other particles. I'm not worrying about any of that. I'm just writing this very general equation of motion. Okay. Let's quickly understand a few properties of this general equation of motion. Okay. So take these equations, and supposing you're in a phase, this term here, constant, alpha minus beta P dot P times P, is like the derivative of a potential that looks like this, which some of you may have seen in discussions on spontaneous symmetry breaking, either in field theory or in condensed matter physics. This is a potential which has a maximum at the origin. So this is this potential. Where is it gone? Excuse me. Slides are in disorder. Just give me a minute. If I take this part and make A negative, then this potential has a maximum at the origin, a minimum on a circle of radius root A over B, root mod A over B, and a max and grows at large B, right? So it's that kind of potential. So that's what this term comes from. If I include gradient terms at energy function, this term comes from them. If I include a coupling between P and the concentration, P dotted into the gradient of the concentration, I'll get this type of term. This is my famous term that I argued is the minimal non-equilibrium term these equations should contain, namely the P advex itself. Attributed, if you like, to the fact that these rotors could actually be moving as they are, I'm trying to show in this picture. equations. Okay, and that was done by Bertin et al. In 2003 for this system. Now, take these equations and let's say you consider a phase where the concentration is uniform and the orientation is everybody pointing in one fixed direction. Okay, and now perturb about that state. So let's say I'm in the ordered phase, all the P's are pointing in some direction that I call parallel, and I resolve the concentration, the fluctuations in the concentration and the orientation into a delta C and a delta P, and I resolve that delta P further into fluctuations along the ordering direction and transverse to the ordering direction.
I just have one small comment. When just to motivate what's going on, we lost you for like 30 seconds. So
oh no,
just,
okay. So
for us
whereabouts was that?
Just tell them about. We were telling about the homogeneous solution. So we're now perturbing around. So going back to the toner 2.
So here's the toner 2 equations.
Yes.
And now a homogeneous solution for these equations with alpha and beta positive is the concentration is any uniform and P is any vector with magnitude right? So now you're hearing me, right?
Yeah, we actually lost you again at the same time. Yeah, we lost you for like 30 seconds continuously. I don't know why.
There's a sensor operating and preventing me from telling you the truth about these equations. All right, so let's, how about now? So look at this term. This term is 0 if P squared equals alpha over beta, right? And this term is 0 if P is spatially uniform. This term is 0 if the concentration is uniform. This term is 0 if P is uniform. This term is 0 if P is stationary, right? So a spatially uniform concentration and P pointing everywhere in the same direction with magnitude determined by alpha over beta is a uniform stationary solution of these equations. Now we heard?
That's perfect.
All right, great. Now we perturb about that state. Let the perturbations be delta C and delta P, and I can resolve delta P into delta P along the mean ordering direction and transverse to the mean ordering direction. I can do another thing, which is if I look at this equation, I've got a P dot grad P. Let me for simplicity assume that lambda is 1. So the speed at which P is advected and the speed at which the concentration is advected are the same. That's not the most general case. And in some ways, it's important to respect that difference, but it's not crucial. We'll set lambda to 1 for the time being. In that case, the flock is moving at a speed, at a velocity determined by P, velocity 1 determined by P. There is the local velocity of the flock is P. And if I co-move with that local velocity with magnitude alpha, a root of alpha over beta, then this equation will just become this. Right? If I just perturb this equation will just become this guy. This equation will become this guy because the only term, because I co-moved with this term on average, this term I'll resolve into P prime of C times the gradient of C, which is what I've done here. And more important, whenever I have a vector whose length is strongly preferred to be fixed, only the transverse fluctuations of that vector matter. If I don't think I have, unfortunately, I don't have a cartoon of that here, and I dare not try to use my draw facility because it will make everything hang. So I don't know if you can see, if you can see my hand. Imagine you've got a vector like this. So imagine I've got a vector like this, and I perturb it like this. The component of this vector along the original vector is second order in the angle. The component of this vector transverse to the original vector is first order in the angle. If we do a linear theory, therefore, I'll only need to worry about the components of the perturbation perpendicular to the mean ordering direction. That's delta perp. So I don't need to worry about delta P parallel if I'm doing a linear theory for perturbations about the state. And I'll get this equation for the concentration and this equation for the orientation. Rate of change of concentration is proportional to divergence of orientation. Rate of change of orientation is proportional to gradient of concentration. These two guys beat against each other very much like coordinate and momentum, or very much like the density and the velocity in an ordinary compressible fluid, but with a difference. In any case, the result of this is those small disturbances travel as waves. They travel, of course, if I go back to my laboratory frame, everything is moving in the direction of the flock. But if I co-move with the flock, disturbances that vary in the direction perpendicular to the flock, this is wave vector here, will travel as waves. So everybody's pointing that way. If I locally perturb a few guys this way, that way, those things will travel laterally in both directions as waves, with a wave speed determined by the sensitivity of this object P, which is kind of like a pressure to the concentration. This is not the same as ordinary longitudinal sound through which you're hearing the speaker and the loudspeaker in your room. This term, ordinary sound, comes from the interplay of a conserved mass density and a conserved momentum. Interplay of conserved mass and conserved momentum. The continuity equation with the density and the Navier-Stokes, compressible Navier-Stokes for the velocity. This mode is arising not for that reason. This mode is arising because the orientation is a broken symmetry mode. And in this active system, that broken symmetry mode couples to the concentration. So you get these splay waves, right? Notice that you get a splay. This divergence of the orientation is called splay because it's a variation of the orientation in a direction perpendicular to the orientation. So it means, if you can see my fingers, it's an elastic response to everybody's aligned like this. If I splay a little bit like this, those things travel laterally as waves. So these are the splay waves of the tonal 2 model. Okay, that's one interesting property of the tonal 2 model. Another is, if you go back to these equations, you've got a noise here. If you now write these equations, perturbed about the ordered state, again, with noise, you will find that the orientational fluctuations are huge at long wavelength. Okay, so the orientation fluctuations diverge at small wave number, just like they do in the XY model of magnetism. The concentration, because of this equation, the concentration fluctuations are proportional to the orientation fluctuations. So the variance of the concentration also diverges at small wave number. That means a uniformly aligned state, if some noise perturbs it, you get huge fluctuations in the orientation as you would in a magnetic system, and you get huge fluctuations of the concentration as you would never get either in a fluid or in a magnet unless you're near a critical point of the fluid, for example. So because delta P squared goes as 1 over wave number squared in this model, delta C squared within a linear theory goes as 1 over wave number squared. A complete nonlinear theory shows that the variance of the concentration is less severe than both of these, diverge less severely than 1 over wave number squared. But that's a separate issue, which I'll come to in a moment. The aligned state has these very interesting orientational fluctuations and stunning concentration fluctuations. If you numerically simulate a block, you find these fluctuations. I don't know about the current status of really measuring these in a real experiment. I think possibly measurements by Denis Bartolo on flocks in what are called Quincke rotors have also seen these now in real experiments. And the reason it happens is orientational fluctuations are easy because they're a broken symmetry mode. So a little bit of noise excites them abundantly at long wavelength. A long wavelength orientation fluctuation means a long wavelength fluctuation in the particle current. So in this region, you've got a component of the current going inward. In this region, you've got a component of the current going outward. Just resolve these arrows with respect to this direction. So you'll get high density, low density, high density. on a very, very big scale. Easy orientation fluctuations lead to huge fluctuating mass flux. Okay? If you now go back to these equations, you also notice there is this wonderful nonlinearity which I motivated, but then haven't used yet, except to show that the flock on average has a kinematic wave speed. This term, this nonlinear term, couples transverse orientation fluctuations to themselves in a rather subtle way. The result of that is that because fluctuations in the orientation are fluctuations in the velocity, a transverse fluctuation of amount delta p will reach a distance delta p times t in a time t. And so basically, remote parts of the flock interact with each other rather quickly. Another way of viewing it is if you've got a bunch of people moving together, a bunch of agents all moving in the same direction, and you have a little local variation in the orientation, the guys that pointed in a different direction will leave that region, right? If I've got a bunch of things all moving almost the same way and a few deviate, this clump will purify itself by those things that deviated actually leaving the group. Okay? The result is that you get what is called a normalization of the stiffness, that is, the combined effect of this nonlinearity and this noise changes the effective observed stiffness at long length scales in a way, for those of you who are familiar with turbulence, in a way that's vaguely similar to how viscosities get renormalized by turbulence through what is called an eddy viscosity, or in more familiar condensed matter systems like spin systems, how stiffnesses get renormalized by nonlinearities. The result of that is that the response, the restoring torques to orientational disturbance at long wavelengths are anomalously strong. The actual normalized angle variance diverges less strongly than 1 over q squared. If it had diverged as 1 over q squared, the aligned state would have only a very delicate kind of quasi-order known as quasi-long-range order, in which orientations macroscopically have zero order, but the amount of order goes down as a power law of the scale. The renormalization of the stiffness leads to angle fluctuations that are less divergent than 1 over q squared and gives you non-zero long-range order in the influence size limit. These are not calculations that I will go through in this talk. You can read about them in Dono and Tu's papers, 1995 and 98. This works only in two or higher dimensions. And the issue only arises really in 2 dimensions. Okay? So what we've done so far is to take this continuum field theory of a magnet where the orientation behaves kind of like a velocity. The orientation carries concentration, the orientation carries itself, but the orientation tries to align for reasons similar to how a liquid crystal or a magnet tries to enter an aligned state. And this weird hybrid of these two kinds of models led to all these fascinating predictions that I just talked about. However, all of this was for what you might call dry active matter. You've got an aligned state, but you don't worry at all about momentum conservation. If you had a bunch of flockers in a bulk fluid, they couldn't change their orientation and therefore their velocity without transmitting the momentum to the surrounding fluid. So all this cool physics has ignored a crucial feature of flocks that normally affects their life, which is that flocking often takes place in a fluid medium. So what does the fluid do? So this is the issue that we chose to tackle at this point more than 20 years ago. And we wrote down the hydrodynamic equations for flocks in fluid. Now let me, before going, so okay, this is a reasonable place to pause before I plunge into the fluid to see if people have any questions.
I think things are okay from this side.
Okay, so I know this is slightly heavy going for beginners, but I mean, by its very nature, this subject is fairly technical, and undergraduates may only get, if there are any left in the audience, may only get a kind of general feeling for what's going on. But unfortunately, it's in the nature of the subject. So let's talk about flocks in fluid. Before going back to writing differential equations, let me remind you of how things swim. You know, when you swim, let's ignore the density difference between you and the fluid. Okay, you and the fluid, let's say, have the same mass density. that even if there's gravity, it doesn't matter. You won't, okay. So if you have an object like that in a fluid and it swims, the object plus the fluid are a force-free system. Okay, so in other words, you want to write down. Imagine my ambition is not to write down the equation of one object in a fluid. It's to take a collection of swimming particles like this, plus a fluid, and treat that as one system. You know, when you've got particles and fluid, the only conserved momentum is the momentum of the particles plus the momentum of the fluid. The particles exchange momentum with the fluid exchanges momentum with the particles. Whatever a particle does in changing its momentum, it does so by balancing the account books by having the fluid take up that momentum, right? So if you want to write down generalized equations of motion for the total velocity field of particles plus fluid, that is the suspension velocity field, for those of you who come from a chem-eng background, then you want to write down force densities due to the swimming particles whose integral or whose sum is zero, right? Because you want to write down force densities on the combined system, and that combined system is force-free. In that case, you can see why I insist that a swimmer is a force dipole, and you can see it pictorially in these cartoons. If you have a swimmer like this bacterium, which is pushing fluid back with its bundled flagella and moving forward, there's one force density pushing the fluid back, and there's another force density which is the body moving forward. If I have a swimmer that's doing a kind of breaststroke like this cartoon of an alga, a chlamydomonas alga, it's pulling fluid towards itself with these two filaments, these two flagella, and its body is moving forward. This guy, therefore, is a force dipole with the forces putting outward along the body axis. This guy is a force dipole with forces pulling in along the body axis. Okay. You can also imagine a passive rod, which, if placed in a flow field, will of course have a force dipole proportional to that flow field's velocity gradient itself. But that's of no concern to us directly. This and this are the guys we're concerned with. So supposing you want to build the hydrodynamics of a fluid, either composed entirely of objects like this, or a fluid in a suspension with bulk fluid and a bunch of objects like this, you'll write down equations of motion for the orientation of these guys. That may be a vector describing, that may be the co-straining of a vector from the tail to the head of these objects, or it may be a traceless symmetric tensor simply describing the average of all the axes of these particles without worrying about head versus tail. That's this. This is a vector, that's a traceless symmetric tensor. And there'll be a joint velocity field of particles and fluid, which I'll call U, or the corresponding density of momentum, which will be mass density times U. There'll also be a concentration of the suspended particles. Okay? Now, what you know is that that equation will be some kind of modification of the equations of a dead liquid crystal. Now, I will not sketch out in detail the equations of hydrodynamics of a dead liquid crystal, except to say that you will have a term for the rate of change of this momentum density, which will come from some coupling to an energy functional describing the cost of deforming the orientation. And there'll be some stresses arising from the elastic torques that reorient these guys if they fall out of line. Then there'll be a damping of the momentum. If there are velocity gradients, you'll damp out those velocity gradients through a viscous damping term, which I've indicated only schematically here. There's going to be Laplacians and so forth, which I've not written. Okay? That, and possibly there'll be thermal noise. That would be the equations of motion of a dead bunch of rods with a tendency to align for steric reasons and a viscosity for the system as a whole. And there'll be a pressure, and there'll be possibly a coupling to the concentration of these particles and so forth. All I'm going to say is that whatever equations those are, I know I have this sort of secret formula for how to modify those if I have an active system. I'll say the magic word, terms proportional to delta mu, coming from an off-diagonal coupling of the variables I'm interested in to those hidden chemical variables. That off-diagonal coupling can have the simplest form allowed by the structure of these equations. This is an equation for a vector field. Secondly, this is a momentum-conserving equation. Even when there's biochemical activity going on in the bulk of the system, it's still momentum-conserving, right? I've got a bunch of particles. They've got full fuel tanks, and therefore they're doing things different from dead particles. But they still got to conserve momentum. So whatever I write down has to be, the rate of change in momentum density has to be the divergence of a stress. The simplest stress I can write down in terms of, say, the vectorial orientation of these particles is something bilinear in that vectorial orientation. So I know that I should add terms to this equation proportional to the divergence of P times P. Okay?
Question?
Yes.
So going back to the equation, this is kind of model A type equation in hydrodynamics. It's non-conserved.
I've not put in the various factors of Laplacian and so forth. I was trying to indicate schematically the equations of fluid dynamics. So this should actually be a viscous damping term. It's viscosity times the Laplacian of velocity, which I've schematically written as a damping operator times the derivative of an energy with respect to the momentum density. So this is actually, what I'm trying to say is, take Navier-Stokes for a fluid, put in the stresses coming from liquid crystal elasticity. That makes it liquid crystal hydrodynamics. Give yourself also an equation of motion to the orientation, which I'll show on the next slide. So this is actually not model A, it's much more like model H or something. Okay, so this is, I've got a momentum density and I've got a vectorial orientation field. The vectorial orientation field produces stresses, even in an equilibrium system, due to the elastic torques in the system. Those will set up complicated flows in response to those misorientations. There's viscous damping, which I've indicated here only very schematically. This is del squared of velocity. I'll show it in the next slide. And then I add in these extra weird active terms.
Yeah, just to follow up. So G is trying to be conserved, and this is enforcing a choice on gamma 1, 2.
Right.
And can one write dg as a divergence of so that you write G as a divergence of the right hand side, right?
The rate of change of G is the
rate of change. Absolutely.
Every term on the right hand side is the divergence of a stress tensor.
Yeah, absolutely.
Okay.
But if you were to write dg by dt as the Laplacian, so something like a model B type equation, that would somehow release the constraint on gamma 1, 2 to being a gradient of
No, because the system has to conserve G as a whole, conserve the integral of G as a whole, every term on the right hand side has to be the divergence of something.
Yeah.
So the viscous term will be del squared of the velocity. The elastic stresses are a complicated mess. They're the divergence of some messy tensor involving two derivatives on, this term will involve the divergence of some elastic torque density kind of terms. And then so every term has to be the divergence of something, because every term has to conserve moment. So you don't, the point is, all those terms are not del squared of something. All you can say about each term is it's the divergence of some tensorial object. Okay.
Yeah, got it. But I was just making the comparison with something that is the Laplacian of something else.
Right.
And that would somewhat release the choice of gamma 1, 2 being a gradient of PP, right?
No, you'd still, the gamma 1 term, meaning what I'm saying is the gamma 1 term, the active force density, the minimal active force density here isn't the Laplacian of anything.
Yeah, okay, fair.
Right, that's the point. There are also Laplacian terms, they'll come in at next order. It turns out that the lowest order active term you can get here is one factor of grad dotted into PP.
Yeah, thank you.
Yes. And so you get this. Now, what I've done here is to write down the hydrodynamic equations. Now you can kind of see what the equations look like. I should also tell you the following, that this idea of the active stress being bilinear in the orientation just comes from taking an object like this, writing down force densities, saying there's one little point force here, one little point force here, or one inward pointing point force here, one inward pointing point force here, and then co-straining up from that. with absolutely no trouble and with minimal algebra, you find that you get a stress proportional to P. You find that you get a force density of this form. Okay, so you can do it microscopically, you can do it on general symmetry grounds, saying it's what's allowed. Regardless of how you do it, you get this feature.
Do you mind if you refer us to some work where this has been done explicitly?
Yeah, so I mean, actually, I guess the first place it was done was in our very, at this point, rather old paper by Aditi Sinha and myself, 2002, Mr. Letters. But if you look up our Reviews of Modern Physics article by Christina Marchetti, a whole bunch of us, Joanny, myself, Jaco, Aditi, Madan, and so forth, that review article has all of this spelled out in great detail. So there is one place where you can read about this in more detail than you might ever want to. That's Reviews of Modern Physics by a bunch of us, 2013. I thought I had that reference, but I seem to have left it out. Yeah, Reviews of Modern Physics, 2013. There's also a shorter and maybe more accessible article by me in Annual Review of Condensed Matter Physics, 2010. There's a whole bunch of such. This field, unfortunately, is overpopulated by reviews. So if you look at my homepage, you'll find a bunch of references, actually.
Thank you.
So therefore, the dynamics of a flock in fluid is, okay, now let me just again let's remind ourselves. If it was a dry flock, the equation of motion would look like this. Where is it? Forget about the details. No, sorry, it's not. Yeah, with a dry flock, the equation of motion would look like this. You'd have rate of change of P advex itself, and you have this term coming from the free energy, which will have, powers of P and del squared P and all that. A flock in fluid has something much richer. You've got the del F over del P term like before. You've got rate of change of P. But now, because there is an ambient fluid, P is advected. So this script D of T is the co-moving, co-rotating derivative. Okay? So it's co-moving with two things. It's P advex itself, U advex P. I'm sorry, I've stuffed everything into this. I don't know. I think on a later slide, I probably have it in more detailed form. Okay. So you've got the original dynamics, which is partial P with respect to T is del F over del P. You've also got buried in here P dot grad P. You now have couplings to the flow. Those couplings to the flow are of two kinds. One is if there is a local vorticity in the fluid, that will rotate P. And the other is if there is a local extensional flow in the fluid, that will align. Then in the momentum equation, you have all the inertia terms which I have left out on this slide. You have these terms, basically, which I have left out on this slide. And you have viscous stresses, active stresses, and pressure, elasticity, and noise. Okay, so the dynamics differs both from a dry flock and a dead liquid crystal. It differs from a dry flock in having all these couplings to flow buried in here and here, and it differs from a dead liquid crystal in having this extra piece in the stress. Okay, so there's quite a history to these ideas, but as far as I know, we were the first to write down these equations, and the Dresden and Paris group wrote the same things down a few years later. And actually, there's a lesson here also. We were trying to write down equations to describe a collection of organisms swimming through a bulk fluid. The Paris-Dresden group were trying to write down equations describing what happens inside one cell. So their orientation field was the orientation of the cytoskeleton. Their active processes were the movement of molecular motors on the filaments of the cytoskeleton. So they were viewing the inside of one cell as a living liquid crystal. We were viewing a whole flock of organisms as a living liquid crystal. And we wrote down the same equations. So for students, that's a lesson in symmetry. When you have a problem in which you have variables with a certain symmetry, here there were orientation variables, either uniaxial tensors or vectors. And you had a momentum conserving system, you had fluid flow. Inevitably, you land on the same equations. Orientation, fluid flow, activity. Those three ingredients take you to the same equation, whether you're trying to write down a fish school or trying to describe a cytoskeleton or anything in between. So that's a nice lesson there. Okay, so these are the equations. What do they tell us? So the first question we can ask is, supposing you take these same equations. Yeah? Is there a question?
No.
All right, yeah. So you take these same, remember, what I did for the toner 2 problem was I just had partial P with respect to T. I had dP over dt, I had P dot grad P, and I had H, which is del F over del P. Okay? I took those equations and the equation with concentration in that case and perturbed them and showed you various interesting properties. I'm going to do the same thing here. I'm not going to worry about the concentration. That's an interesting but inessential complication. Let me just take the equations to the orientation. I now have to perturb a different equation. I have to perturb an equation in which the average state is that all these things are swimming through the fluid. And I'm going to sit in the rest frame of the combined system of particles and fluid. So in that rest frame, the orientation is some non-zero vector pointing in some direction. The suspension velocity field is zero because I'm sitting in the rest frame of this system. So I'm going to perturb about that state. Okay, so, and I'm going to do it in the following rather cheap way. I'm going to ignore the inertia of the system as a whole. This is a perfectly good thing to do on length scales that correspond to what goes on inside a cell, or even length scales that correspond to what happens in a suspension of microorganisms going through a fluid. If you're below, in the case of the cell, it's fine. Even for microbial suspensions, if you're below about a millimeter or so, you're good. You can ignore inertia. Okay. I don't want to launch into a side discussion on fluid mechanics and Reynolds numbers. Basically, the effective Reynolds numbers for velocity fluctuations at scale up to a millimeter are too small in these systems for inertia to matter at all. But I'll show you shortly that unsteadiness can matter even in these systems at modest length scales. I'll come to that. What I'm going to do here is, because the velocity equation isn't a dynamical equation with rates of change, it's like an instantaneous, Stokes hydrodynamics, for those of you who know it, is weird for the same reason that Newtonian gravity is weird. In Newtonian gravity, you tell me where the masses are everywhere, and I'll tell you the gravitational field everywhere at that same instant. Obviously, that's an approximation. Even Newton knew that there was something potentially problematic about that approximation. But that's a side issue. Similarly, steady Stokes hydrodynamics is an approximation in which you specify the force densities everywhere, and the Stokes equation tells you the velocity field everywhere through the equation Laplacian of u equals gradient of pressure plus other force densities. Okay, so it's a description that's good, that says that the velocity field relaxes so quickly because viscous relaxation is so fast compared to other processes, that on the time scales of interest to other processes, you can treat the velocity field as being determined instantaneously everywhere. So we take the velocity equation, we say its rate of change has always quickly become zero. I solve this equation for the velocity in terms of the orientation, plug that solution into the velocity gradient terms in this equation, and get an effective equation of motion for the orientation. What I find for perturbations about a uniformly aligned state is that that equation predicts always an instability. And it's a very weird instability. It says the rate of change of orientational fluctuations has two pieces. One piece coming from the liquid crystal elasticity, which is buried inside this. This term says that if you've got an orientation in a viscous fluid, if you have spatially varying orientation in a viscous fluid, it relaxes at a rate given by the elastic constant divided by the viscosity times wave number squared. So if I had a dead liquid crystal in a bulk dead liquid crystal, its orientation field relaxes in a sense diffusively with a diffusion constant given by elastic constant divided by viscosity. This kinetic coefficient for the orientation is also basically an inverse viscosity. If I include active processes, I get a term in here which depends on the angle between the direction of the wave vector of the perturbation and the mean ordering direction. But its magnitude does not depend on the wavelength or the wave vector of the perturbation at all. This is a result of the very singular nature of Stokes hydrodynamics. And because the active elastic stresses, you see, what comes into this equation is gradients of the velocity. Del squared of the velocity is of order 1 gradient on an angle. So 1 gradient on the velocity is of order no powers of gradient times the angle. So you end up getting that the orientation relaxes in a wave number independent way in an infinite system. But crucially, its relaxation rate is strongly direction dependent. It's got this incredibly important factor, cosine of 2 theta, coming from imposing incompressibility, which I forgot to write down here. I apologize, I didn't write it down anywhere. I'm assuming that all speeds of all these creatures moving through the fluid are much, much, much smaller than the speed of sound in the fluid, which is a very safe assumption. The speed of sound in water is about 1,000 meters per second. Even a barracuda swims at only a couple of meters a second. And certainly a microbe swims at a few microns a second. So you're absolutely safely below sound speed. So you can treat the suspension as incompressible as regards the total density of the suspension. And therefore, imposing incompressibility, that is divergence of u equal to 0, is fine. I do that, I solve this equation, insert there, and I find the orientation relaxes in a wave number independent but wave vector direction dependent way. The coefficient here, sigma A, is the sign of the intrinsic force density associated with these particles. It has one sign for pushers like this guy and the opposite sign for pullers. I've changed the name from sigma 0 to sigma A, sorry. If sigma A is positive, that's for these swimmers. I unfortunately called it sigma 0 negative, but notational change, sorry. Then this coefficient will be positive for wave vectors close to the wave vectors within a 45-degree cone of the ordering direction. If sigma A is negative, that is for the polar swimmers, it will be unstable in a range of wave vectors outside 45 degrees to the ordering direction. Okay? And the point is that at small wave number, at long wavelengths, this term is order 1, this term is order wave number squared, so this term always wins. So a bulk active Stokesian suspension is always unstable. So a collection of bacteria in bulk fluid with the best will in the world, if they want to align with each other, can't align with each other because if a slight perturbation arises, the counter flows, secondary flows that the stresses coming from that slight perturbation set up always disrupt the orientation. Okay? Here's the picture. Imagine you have an aligned state, and imagine you have polar swimmers, and you have an aligned state, like everybody pointing in that direction. Okay, then if I perturb that state with a splay perturbation, then the force densities are closer together here than here. So the pulling is stronger here than here. So you will pull fluid up this way. In this region where the splay is opposite, the force density has been pulled together more here than here. Therefore, the pulling is stronger here than here. So you will suck fluid that way. This region in between, which you perturb by tilting it this way, will now get further tilted that way by the velocity gradients set up by the flows in response to the perturbation. The same argument, changing things suitably, if you have pusher swimmers like this guy, same argument arises here. If you have a bend perturbation, then the force densities are closer together here than here, and they're closer together here than here. So it'll pull the flow this way, and it'll squeeze the flow that way. And this perturbed region, which was already tilted this way, will get tilted more in this direction. So bulk, active, pneumatic, and you can keep track of the fact that the ordering is a vectorial order, not merely an axis, but it knows head from tail. That doesn't save you. You can include the elasticity. That will only save you at short length scales. This term is bigger than this term if kq squared is large this term is bigger than this term if sigma over A is bigger than kq squared. Sigma over mu is bigger than kq squared over mu. That is, if sigma is bigger than kq squared. That is to say, there is a length scale in the problem, which is the square root of the ratio of the elastic constants to the active stress. Remember, stress has units of force per unit area. Elastic constants for a pneumatic liquid crystal in 3 dimensions have units of force. This ratio, therefore, is a length squared. Its square root is a length. That length tells you that on length scales bigger than this scale, this guy wins over this guy, and there's nothing you can do about it. And the growth rate is the single intrinsic time scale defined by the ratio of viscosity to active stress. Okay. Anytime you have a system with a scale of viscosity and a scale of stress, there's a single natural time in the problem. If you have a gel and you ask, if you squeeze a gel macroscopically, a polymer gel, how does it relax? It relaxes with the relaxation rate given by the gel modulus divided by the viscosity. Okay. So, the relaxation of objects within elastic modulus, within a translational elastic modulus and viscosity and no inertia also has a wave number independent character in this sense. Anyway, so aligned suspensions, it looks like you can't make aligned active liquid crystals. Okay. The real story is even more subtle and even more complicated. It was worked out only recently by Ananya Maitro in a paper which will come out in Nature Physics next month sometime. It's very interesting and I commend it to you. But roughly speaking, what I said is true. And in more detail, if you work this analysis out in 3 dimensions, because in 3 dimensions, there are 3 kinds of liquid crystal deformations: splay, bend, and twist. It turns out there are 2 kinds of instability modes. The one I just sketched for you in these cartoons, which interpolates between splay and bend with this kind of a relaxation rate, this guy, and another which interpolates between twist and bend with this kind of relaxation rate. For a given sign of the active stress, you will always go from a range of angles in which there is an instability to a range of angles in which you are free from the instability, because cosine 2 theta changes sign at 45 degrees. The bend twist mode is always unstable for pusher swimmers, no matter how wide, at what angle you go to. Okay, the bend twist mode is not mitigated by an interpolation to splay, and so this is what should dominantly be seen in 3-dimensional pusher suspensions. So if you have 3-dimensional suspensions of this type of swimmer, they should always be you should see an abundance of twist in addition to bend, and that is indeed the case in numerical simulations of such systems. Okay. Okay, so that's the story. And this picture is abundantly confirmed in experiments on length scales from inside. This is the nucleus inside a single cell, which is actually rotating because the instability that I just talked about has set in the cytoplasmic fluid around the nucleus inside the cell. These are experiments by the Barcelona group, Francesc Sagués and company, and they observe the instability we predict by templating an active suspension on a background aligned liquid crystal and then watching the instability set in. These are a very special active suspension made of microtubules, molecular motors, ATP, and some depletant to make the microtubules meet each other and produce extensile flow. And they observe exactly the bend instability that we predict. So this is cool. The end state of the bend instability is a thing called active turbulence. Finally, it goes into this. I don't think I have a movie here. Yeah. It goes into this state called active turbulence, where basically on big length scales, there's no vestige of even the underlying liquid crystalline order left. You see basically the system constantly shearing itself. You see, if you start on a line state, you see this instability. This instability resolves itself into defect pairs of opposite sign, which move outward. They further go unstable, and you go into a spatiotemporally chaotic state called active turbulence. It's turbulence not driven by Reynolds number, but driven by a competition between these two rates: the growth rate of the instability and the elastic relaxation rate of the orientation. And this guy is unable to win at big length scales over this guy. And so you get that instability on length scales above this so-called active length, which is the ratio of the pneumatic elastic modulus to the active stress, square root of that. And that's active turbulence. And active turbulence originates in this instability that we predicted 20 odd years ago. And there's loads and loads of beautiful experiments that will now confirm that. It'll be interesting to know how to escape this instability. One of the ways to do it is to note that, okay, so are there any questions before I go further?
Yes, I have a question, if I may. If we were to model a rod-shaped cell, in that case, would we have two equations, one for the orientational tensor and then one for the polarity?
Sure. So if you had, I mean, that depends on actually the manner in which the cell has got polarized. But in many systems, there are, for example, if you take, as an example of a rod-shaped cell, if you take a rod-shaped bacterium, or if you take, I don't think I have a picture here, but let me see if I can find one. Just give me a second. I'll come out of this talk and go to another talk. If, for example, one second. Excuse me, finding it. Yeah, I guess. It's not a great slide, but this is an epithelium of elongated cells. The cells, in this case, as far as I know, don't have any head-tail difference. They don't have a motility, but they're active in the sense they are actively contractile or actively extensile. So if you have cells of that sort, I don't think you need to introduce a vector at all. It's enough to introduce just a uniaxial tensor. If, on the other hand, you have a system like, let me see if I can find this. You have to give me a moment. Yeah, there's experiments on neural progenitor cells in which the cells actually do move systematically in one direction, but they seem to be able to shear past each other so strongly that even though an individual cell has a polarity and has a velocity, the interactions are such that the polarities don't seem to align and only the axes align. So you might need to keep track of a polar vector to describe the current of the particles. But in fact, these systems seem to be dominated by the nematic properties itself, even though the individual cells have a polarity. So it seems to depend a lot on the degree to which the polarity is able to produce some coherent local polar order on a scale bigger than a few cells. That's maybe, it's a complicated answer, but it's the best I could do. I hope that's some use.
Yes, thank you.
Right. Yeah, so now you can ask about ways in which you could produce ordered states of active orientable things. One way is to note that this whole instability story came from Stokes hydrodynamics, from the long-range character of Stokes hydrodynamics, where the velocity field here is determined by the force density everywhere through an inverse Laplacian, which is something decaying as 1 over r. If you take this same system and confine it between two plates, or absorb it tightly onto a substrate. So let's look at this system. Imagine you place it on a two-dimensional surface, let us say a glass slide, and you put a cover slip on top. So you have a base and a lid. That base and that lid give you a preferred rest frame. You can the effects of momentum conservation are clearly greatly mitigated because the base and the lid are now a momentum sink for the system. If you look at it laterally, the long-range character of the, so now I'm looking at, this was a top view, and this is a plan view, if you like. I'm looking sideways. Imagine you've confined it between a base and a lid with a small gap between the two, and this is where my active system is sitting. Then the hydrodynamic effects of one region here on another region much farther away than the gap thickness are highly screened. Okay, so you might guess that the hydrodynamic interaction gets screened and you don't have, and basically therefore that what happens is that this damping proportional to del squared u is simply replaced by a damping constant times u with no wave numbers, and the velocity at each point is determined locally by the active forcing at each point. Okay? Because del squared is the Laplacian, which is the square of derivatives along x, y, and z. And the z direction here I've taken to be narrow. So I can replace del squared by 1 upon the thickness squared. And now the wave number dependence has gone away. And you might think everything is local and very simple. The truth, even for this system, turns out to be more interesting than that, as we showed a few years ago. A 2D confined, if you take a bulk active fluid and confine it between two walls, thereby seemingly screening away the hydrodynamic interaction, you do not go back to the tonal 2 model. You get something a little different. Okay, and the reason for that will be apparent on the next slide. Okay. What I have to do now is I agree that the viscous damping can be, my Stokes equation now becomes damping times u, where this damping is basically viscosity divided by that gap thickness squared. I don't know if I mentioned it anywhere, no. The coupling to flow now says that if locally I've got a polar orientation of these swimmers, that gives me a local forcing proportional to their orientation. I then have elastic forces coming from the liquid crystalline elasticity of my system. Okay. I have an orientation equation which has the following interesting property, that if locally I have a velocity pointing in a certain direction, it favors the orientation pointing in the same direction and can relax through its own elasticity. But this velocity field is not unconstrained. The bulk velocity field was incompressible. After I confine, there's essentially no flow in the vertical directions. The velocity, the effective projected two-dimensional velocity field obeys incompressibility. That introduces a long-range constraint, which results in a very surprising equation for the orientation. Basically, what you end up getting is that long wavelength fluctuations, let's say theta is the angle of the orientational fluctuation. If I resolve it into wave numbers, long wavelength fluctuations in the orientation relax at a rate that again depends on the direction of wave number of the wave vector, but not its magnitude. So you get a mechanism which is actually akin to the Higgs mechanism. The Higgs mechanism makes the broken symmetry mode in it gives a mass to the broken symmetry, the number Wolfstone mode. The same kind of thing happens here. This orientation field relaxes at a wave number independent rate. Okay, so orientational fluctuations are exceptionally small, and the system has long range order. This is a very technical thing. It's just to point out, you just take those equations, confine them, ask for the effective equations, you get this funny physics. For the algebraic details of it, I commend you to this paper by a bunch of us a few years ago. I won't dwell on this longer. I want to go to a different problem. You know, after all, from experience, that even though I've told you all this stuff about flocking being in fluid being impossible, you've seen flocks, whether actually in the ocean or in television programs. You've seen macroscopic flocks on a huge length scale. No sign of the instability that I'm talking about on big flocks. So clearly, swimmers with inertia are able to escape the kind of instability I'm talking about. Some important work on swimmers with inertia is done by Eva Canso, Mike Shelley, and others. But they work in a regime where they almost completely ignore viscosity and keep track only of inertia. What we want to know is we want to start from viscous hydrodynamics and ask, is there a way that if we keep track of the fact that our swimmers actually have a velocity, under what circumstances can they outrun this viscous instability, outswim this viscous instability? I don't want to go to very large, very fast swimmers and keep track of inertia-dominated hydrodynamics. I want to perturb gently away from purely viscous hydrodynamics. Keep track of what extent, to what degree do we need to take inertia into account, and to what degree does the fact that the orientation field is a vector rather than just an axis, how does that make a difference? Okay, so that's what we want to do. You recall I told you that active polar hydrodynamics without inertia, purely Stokesian, has this instability. If I include only the fact that the swimmers are moving, then all I'll be including is the fact that the orientation advects itself. All that does is to change our original instability into a piece coming from here, which says that perturbations don't just grow, they travel as they go. However, it doesn't change the fact that the eigenvalue of these perturbations has a positive real part for some directional angles. It merely moves the instability. Okay, so at this level, including only polarity and only motility into Stokesian active polar hydrodynamics doesn't really buy you anything. And this was already understood in our paper back in 2002. Now, let's do the following. We also showed back in 2002 that if you took these same equations, retained inertia, but forgot viscosity, retained inertia only at the level of unsteadiness, didn't worry about u dot grad u, the famous nonlinearity of the Navier-Stokes equation, just kept unsteadiness. Then the coupled dynamics of orientation and velocity gives you something with a completely different dynamical structure. It gives you, now you've got dp over dt equals these things coming to velocity, and rho del u over del t is equal to these active forces. So P and U beat against each other in a non-trivial way, And you actually get the effective equation of motion is P double dot is Q squared times cos 2 theta times delta P. Okay? And that has a very different structure because that says that now again, you've still got this fatal cosine 2 theta. Okay? I know it must be difficult to follow all this algebra, but I'm doing the best I can without facing you and without a blackboard. This says that if I replace d2 over dt2 by minus omega squared, this says that omega squared is minus q squared times cosine 2 theta, right? With a coefficient which is the activity. So this is a mode which, depending on the sign of the active stress, either above 45 degrees or below 45 degrees to the aligning direction, will give you omega squared equals q squared with a minus sign. That is to say, you will get a growing mode, and it will be a growing mode with a growth rate linear in wave number. Okay, that means the time on a length scale, or on a length scale 1 upon q, the time it takes the perturbation to grow by, let us say, to grow exponentially by 1 factor of e, that time is proportional to the length scale you're looking at. And so there's a kind of invasion speed. Once you include the density, there's an invasion speed of the active instability, schematically proportional to the square root of the active stress over the density. Right? Remember, stress over density has units of speed squared. Right? So this is an invasion speed of the instability. So now you can ask, if I combine this and this, remember, motility has a speed, V0. I've now argued that the active instability, when unsteadiness is included and viscosity is forgotten, has a speed, which is an invasion speed, root sigma over rho. Let's put those together. Okay? So maybe what will happen is that the ratio of this speed and this speed will matter. And maybe, okay, it's important to note that it is very crucial to include the density. If I work with the Steady-Stokes equation, this speed is infinity, and no one can outrun it. The moment I introduce the density, the old instantaneous Stokes instability becomes an instability in which there is actually a length scale, a scaling between time and length. And on a scale L, the time it takes the instability to grow by 1 factor of E is that scale L divided by this speed. Okay. So now what you do is write down Navier-Stokes for a flock in fluid. I can skip this already. I'll skip all this. I'll go to the effective equation. Just a minute. Yeah. So what I'll do is I now have the equations for orientation written down in full detail. Rate of change of P has a piece from rotation, advection, and shear alignment. S is the symmetric part of the velocity gradient, and P carries itself. Okay, and there's other things which I won't worry about. The rate of change of the velocity, I won't worry about u dot grad u, but I will keep rho del u over del t. Has stuff from pressure, viscosity, and active stress. Okay, these are the equations whose properties we want to look at. These equations contain a crucial non-dimensional number. Remember, I told you, let's go back here. There's an invasion speed and there's a self-advection speed. The ratio of those two can be packed into this non-dimensional number. It's the ratio of the square of the motility to the square of the invasion speed. It's a swim speed squared divided by the instability invasion speed squared. And that's crucial. So we write down these equations. The active stress, again, is proportional to P times P with a coefficient sigma naught. The motility and the strength of the active stress are two independent features of the fact that this is a self-propelled system. Okay? let me skip that detail, but you can imagine, for example, that a swimmer being motile primarily because of a quadrupolar mode of swimming and having an active stress primarily because of a dipolar pushing. And, or you can imagine making a swimmer out of particles with a surface velocity field whose dependence on the colatitude can have a cosine theta, a P1 cosine theta, and a P2 cosine theta. This piece determines the swim speed. This piece determines the active stress. Okay. So now what we'll do is we'll take these equations, and again, I'll perturb them about the state u equals 0 and P is aligned. I've thrown away the concentration just to make life simple for me. So aligned state u equals 0, P that way, perturbed with u is delta u, and P is P0 x plus delta P. And this cartoon tells you why. I can just look at the transverse part, delta P perp. And what do I find? I find a set of equations whose form need not trouble you. But what's cool is that I find that everything depends on how big this ratio of squared speeds is. You can also view it as a kind of ratio of the inertial stress due to swimming and the active stress. But I prefer to view it as a ratio of the motility speed squared divided by the invasion speed squared. What I find is that if V0, and imagine studying this as a function of the swim speed, the motility speed V0. I find that if the swim speed is 0, omega goes as q times the square root of this guy. So if sigma A is positive, then omega has a positive imaginary part. And so you have an instability. If V0 gets, if V0 gets big enough, it competes. This combination, V0 squared minus sigma over rho, shows that this piece has the invasion speed squared, this piece has the swim speed squared, and in principle, if the swim speed is fast enough, you can outswim the instability. The moment V0 gets big enough that this piece gives you stability, you acquire another instability. You get an instability of whose growth rate is quadratic in wave number. So basically, if you're at 0 swim speed, you have the old Stokesian instability with a non-zero growth rate at 0 wave number here. If you switch on a small swim speed, you get almost that, but at very, very small wave numbers, you still have a linear growth rate. It looks like this. It's still unstable, but with this linear guy. If you swim faster, you get rid of this instability, but you still have a growth rate quadratic wave number. If you swim fast enough, it turns out even this goes away, and I can't get that from this expansion. And you have a system which has no instability at all. So you can outrun the instability and a very modest amount of inertia. Basically, if this quantity, which is kind of like a Reynolds number at the scale of the particle, becomes of order 1, all of a sudden you're able to escape that instability. You can ask, okay, supposing I'm in the regime where this instability has been, where I've escaped the primary instability, but I'm still unstable at order wave number squared. What happens? Then you have this, then you have nothing but to take the equations in that regime with all the nonlinearities and study them numerically. We did that, or rather Ryan, my PhD student, did that. And this is actually Aditi's last work. She is no more. This collaboration, Ryan, Navdeep Rana, now at Göttingen, Ryan now at Stanford, the late Aditi Simha, Prasad Perlekar at PIR Hyderabad, came up with a rather dramatic phase diagram. If you're at small values of that crucial parameter, which is 0 at 0 swim speed, and which represents the competition between swim speed and invasion speed, then in the regime where you have the linear instability with growth rate linear in wave number, in effect, you find the system is utterly actively turbulent, and is riddled in this case with integer strength defects because the order parameter is a polar vector. If you cross into the regime where the order Q instability has gone away, but you're still unstable with the growth rate proportional to wave number squared, you find a state that has a little bit of noise, but ultimately retains its order. So as a function of this of motility, you go from defect turbulence to a state with some noise, but where the aligned state preserves itself somehow. Phase turbulence, it's called in the dynamical systems literature. Okay, so you go from something like this to something with a bit of noise, but basically stable. If you're in the order Q regime, you find, wait for it. You find defects start to grow and you get a spatially temporally chaotic state of defects. If you're in the regime where the system is nominally linearly unstable, the perfectly aligned state is linearly unstable. You find that aligned state shows a bit of instability, but ultimately manages to clean itself up. Instabilities grow, and except for some numerical difficulties at large times, you basically get, on average, an aligned state. It's not so apparent from this, but from measurements of the order parameter, it is. So if you measure, this is called a transition from defect turbulence to phase turbulence. And if you measure the order parameter, which is if you take the P field and measure its macroscopic average and then time average it and take the absolute value of that, you find that in low values of this inertia parameter, it's 0. And there's a nice clean onset to a state where P is non-zero. This is a non-equilibrium phase transition driven by motility alone. If you measure the orientational correlation functions as you approach this transition, they become longer and longer and longer ranged. If you measure the correlation length obtained by doing a collapse of this with respect to a single length scale, that is replotting this against R over some length, which you determine by seeing what value of length at each R makes the data all collapse onto a single curve. You find that length grows with R and seems to diverge. I plotted 1 upon that length against 1 upon R, and 1 upon that length seems to go to 0 at a finite, a non-zero 1 upon R. That is at a finite value of R. There seems to be a non-equilibrium phase transition at a value of R of order 1. The correlation length is essentially the interdefect distance. And as you go to larger and larger values of R and approach R equals 1, the correlation length seems to, the interdefect distance seems to diverge. The turbulent state has many interesting properties, which you can measure. The phase turbulent state, the state you get when R is bigger than that first threshold value, has evidence for a state in which the angular fluctuations about the aligned state have properties very similar to what you expect in an equilibrium aligned continuous spin system. You see evidence for the broken symmetry mode. You see it in 2D and in 3D. Okay, and that is where I'll stop today. I've told you an awful lot. I have no idea how much of it you've been able to absorb. It's a bit difficult to get all this stuff into one's head in an online talk without being able to pause and ask questions, but it's the best I could do under the circumstances. So I'll leave you with this. So I'm happy to answer questions.
I just want to thank you, because it's really not easy material to deliver in the setting. And I think they need some time to absorb and go over the recordings probably slower rate and do the derivations at ease. So
yeah, it's somewhat heavy material, I agree, but you know, it's what I do. Okay, so if there are no questions for the moment, I guess I can sign off.
Yeah, I guess.
Yeah.
Yeah, we have one question. Yes,
sure.
One question.
Sure.
So you were discussing sort of different types of equations whereby competing terms appear from one mechanism or the other mechanism. And these are all field equations.
Right.
Is there a possibility to invent agent-based models corresponding to different types of field equations? Can you sort of
You're saying to go backward from, you want to go backward from a field equation.
So you say, okay, there is a particular type of an equation with there's specific instabilities, and this is a field equation, right? Can we invent an agent-based model that would eventually generate that type of behavior? That's an interesting question.
I haven't thought about it, but it seems to me that it should be possible. If you come forward, I can see your face. It'll be nice to actually see who you are. The frame is cutting. If you don't mind.
No, I don't mind.
Yeah.
Just facing that camera.
Yeah, no, you were almost in the camera. Only your head was not. Hi. Okay.
Okay. All right. Sorry. So,
yeah, that's an interesting question. I mean, I think the point is that typically what happens is people either build field equations by starting with a particle model, or people have some experimental system in mind for which they directly write down a coarse-grained theory. But it is possible, I would say it is possible to think up microscopic particle scale models or lattice models corresponding to some of these field theories. For the particular problem I have been describing so far, we actually know what the particle model is. Okay, it's actually aligning swimmers in a fluid, but it'd be interesting to think about particle models. Now, I mean, to give you a kind of offbeat example, you know that people invented the lattice-Boltzmann method as a way of solving the equations of fluid dynamics. And that was an example of inventing not exactly a particle scale, but, you know, let's say you take there was a precursor of the lattice-Boltzmann model was lattice gas automata. So there you had the field equations. You knew that they descended from Newton's laws, but you invented a particle or an automaton model, which was neither the original PDE nor Newton's laws, but a kind of nice numerical solver, which had an interpretation as a kind of particle equation. So there's one historical example of where people in fact did this. So yeah, it's worth thinking about in some other cases. The other thing, of course, that people have been doing is to take experimental data and try to back out the best field or particle equation based on some kind of least biased projection or something. So but that's a different game, because there you're taking experimental observations and trying to do this. So it's not quite the same thing. But yeah, it's worth thinking about.
Okay, thank you. Yeah, I'm fine. No, I'm fine. Thank you. Thank you.
Okay. If there's no other questions, I'll say goodbye and meet you guys tomorrow.
Yeah, I guess no more questions.
Yes, yeah, bye.
Thank you.